Problem 14.65 involves a nozzle shown discharging water at a rate of 40 foot cube per minute into this system right here. Knowing that at both A and B, the stream of water, A right here, B right there, the stream of water has a velocity magnitude of 75 feet per second, and neglecting the weight of the vane, determine the components of the reactions at C and D. I've labeled some terms around here like theta is equal to 60 degrees right there. This height of 20 inches I'm going to call lowercase h. 3 inches right here is lowercase l, and I'm going to set this 15 inches here equal to capital L. We're told a flow rate here of a volume per unit time of 40 foot cube per minute, and we've got a speed of 75 feet per second at both A and B, and all the way through the system here. And there's the symbols for L, little l, and H, and theta, and what they're equal to. Going down through here, we're going to need dm/dt in a minute. So if we take the volume per unit time multiplied by the density, the mass density, that is, mass per unit time, that will be our dm/dt. Notice when we do that, the V over T is 40 foot cube per minute, and the density of water is 62.4 pounds per foot cubed. To make it a mass density, we divide by G. And so when you put all these numbers together and put 60 seconds in for a minute, you'll end up with 1.292 slugs per second. And I'm going to store that in my calculator. Go back up here. If you look at the pinning, the way this pinning is done, the only kind of force that you can have at C is in the Y direction. So C sub x is going to be 0. Because the way this is pinned here, we have a dx and dy component. Now I'm going to look at the linear momentum and angular momentum for the system. It's not conservation of these quantities. First of all, we'll look at the linear momentum in the x direction, and we start off with the general expressions Lx1 plus the sum of the force in the x times delta t is equal to Lx2. Now what is my Lx1? Well, it's a system of linear momentum in the x direction that you have for everything that's in the flow here. And then you're going to have a delta m of mass entering down here at a velocity v sub a, and the x component of that delta m v sub a is going to have a cosine theta associated with it, and then plus your summation of the forces in the x, and left the sub x off there, but it should be right there. So the force of the x times delta t then is equal to Lx2. Well, Lx2 is the linear momentum of the system in the x direction plus the linear momentum of the delta m coming out of here in the x direction. That's just delta m times v sub b. Of course, the linear momentum of the system cancels out on both sides, and you can solve for dx out of this because this is what your force is going to be. You only have a dx force here. And so if you divide through by delta t, you'd have a dm dt and a v sub b right here, and then you bring the VA cosine theta to the other side, and you have a minus VA cosine theta right there then. And so that leaves you with just the sum of the forces, which is just d sub x in this case. So you end up with dx equal dm dt of vb minus va over cosine theta, or times cosine theta. And that comes out to be 48.4 pounds. Now we're going to write down the expression for the y momentum, and that's the system momentum of y plus the delta m momenta, which is going to be a VA sine theta, plus then the sum of the forces in the y direction times delta t, and that's equal to the system momenta for the y direction for the system. And you don't have any delta m moving in the y direction, so you got a velocity, or excuse me, momentum 0 for that part of that term right there. So when you look at all this, and divide through by delta t, you're going to have a dm dt and a VA sine theta right there, and a minus sign because you're going to put that on the other side of the equation. The system momentum, if I didn't say it already, is canceled out on each side. And so what you're left with is some of the forces, which is dy plus cy right here. And I'm going to call that equation 1 because it's got two unknowns in it. Now we're going to look at the angular momentum, and we're going to calculate that about point D up here, right there, okay? So as we look at that, angular momentum at 1 plus the sum of the external moments times delta t is equal to angular momentum at 2. And what I'm going to do here is look at the system's angular momentum plus the delta m and what angular momentum it has coming in here. And what it has is you break it into two components. It has a delta M V sub A cosine theta for the x part at a distance of h plus little l from D right here. And then you have the y part of that, which is going to be a delta M V sub A times sine theta, and it's going to have a moment arm of L, capital L right there. And it's a minus because this one's trying to produce a clockwise moment, and this one right here is trying to produce a counterclockwise. And then you got your plus the moments, the external moments right here of c sub y, assume it's upward, and it's trying to produce a clockwise moment at a distance L right there. So that's why you have a minus c sub y times L times delta t. And that's got to equal to the angular momentum of the system about D afterwards, plus the delta M and its angular momentum about D, and it's trying to produce a clockwise moment across around there. So that's why it's a plus, and it's going to be delta M V sub B times little l, because the moment arm for it is this distance right here, little l. Okay, when you plug your numbers into this equation right here and solve for c sub y, you find that's minus 29.01 pounds, so it means that it was downward instead of upward. And when you plug that number back into equation 1 right here and solve for d sub y, you get a negative 54 pounds, 54.9 pounds, and it's also downward as well. That's not unexpected in the sense that you're pushing water against this. You'd expect this to push back and this also to push back.